Would you like to have real-time femtoamp measurement capabilities like this on your desktop? Maybe you could if you spent $10,000 for a Keithley electrometer, plus accessories from them like a low-noise triax cable and a computer interface with plotting software. If you don't have that kind of money, maybe I have a solution for you. I have been designing electrometers for over 45 years and have seen significant improvements in their design. After many years of research and development, I have designed an electrometer that uses no high megohm resistors, no range-changing components, and has increased accuracy and reduced size by using surface mount components. This new square root electrometer has the following advantages. The input current is less than 5 femtoamps from a CMOS amplifier source to ground. The input voltage burden is less than plus or minus 20 microvolts. The input is protected from transient voltages. No high megohm resistors are used that have Johnson noise and temperature drift. No range-changing spikes from 1 femtoamp to 1 microamp. The input current source noise determines the effective minimum noise of the electrometer. Very accurate to 0.1%. Time constant of 50 milliseconds or faster from 1 microamp to 700 femtoamps. The output time constant of the electrometer is a constant 11 milliseconds plus the variable time constant of the input logging transistor. The 1 picofarad capacitor across this transistor for circuit stabilization reduces the time constant of the electrometer to 25 milliseconds at 1 picoamp input current and continues to get slower with reduced input current. Includes a 24-bit ADC and a USB interface with all supplies and references. The only power required is the 5 volts supplied by the USB port. Very small size because only surface mount components are used. Very low cost. My electrometer is very low noise because the high megohm resistors have been eliminated. This not only reduces cost and complexity, but also eliminates the Johnson noise produced by these resistors. The noise of this electrometer approaches the theoretical shot noise limits based on the bandwidth and measured current. I will now start a plot using my desktop plotting software simulating a digital chart recorder with a full scale of 1 picoamp. I am plotting a 10 Hz signal of 500 femtoamps with a noise level of approximately 6 to 8 femtoamps. The current source used is a 200 gig high megohm resistor using an EDC voltage standard. I will make 10 50 femtoamp steps from 500 femtoamps to 1 picoamp. I will now step down to 500 femtoamps and make 50 femtoamp steps down to a level of 50 femtoamps. The final step is to a level of 10 femtoamps. Pressing the escape button will save the real-time data to a file. I will now display the file with my data file viewer software. This software allows me to zoom and expand the data and quantify the noise at any place using the zero difference value keyboard command as indicated in the help menu. Just move the cursor to any point, press the Z key, and move the cursor to measure the difference. Some plots have a large dynamic range like this one that shows 6 current steps from 10 femtoamps to 1 nanoamp. When this type of plot is displayed using a linear current scale, only 3 steps can be seen. To better see this plot, I've included a log scale display command to display the graph with a log current scale to see the entire range of the plot at one time. If you expand the Y scale, you will see a 10 femtoamp step and a 1 million femtoamp step, a nanoamp, at the same time. Any point can be zoomed into and quantified using the zero difference value command, then moving the cursor for a relative measurement. The relative measurement is displayed as diff equals at the top of the display. I will move the cursor to point 1307 and press the Z key to zero the diff display. I will move the cursor to point 1300 and note the diff reading of 4.232 femtoamps at an input current of 105.13 femtoamps. Pressing F4 will bring up my noise calculator that combines the Johnson noise of the current source resistor with the shot noise of the measured current and calculates the total noise at the calculated time constant of the electrometer. I am now using a 10 gigohm resistor in my current source that has a Johnson noise of 5.2 femtoamps at a time constant of 244 milliseconds. I will now move the cursor to point 1000 and measure a difference current of 1.0005 nanoamps at an input current of 1.0006 nanoamps.